let's remember the chain rule. So I've got just a few notes. You can follow along on this part, and when I get to something new, I'll try and remember to tell you. But in Calc 1, we had a chain rule as well. So basically, you know, if we had u being some function of x, then we could say that the derivative of f with respect to x, we could kind of split it up and say, hey, that's derivative of f with respect to u first, because u is a function of x, times the derivative of u with respect to x. So we kind of had that middleman there, that we could do that, and then those kind of cancel out, and really we're left with df dx, which is what we're looking for. So let's just remember how we did one back then, and then we'll look how we do it with partial derivatives as well. So anyway, if we have, you know, example, I'm still using red here, that's okay, f of x equals, you know, 3x squared minus 5x plus 2 to the 8th power. Well, what we can do there is we can say, hey, let u equal, you know, what's inside there, so 3x squared minus 5x plus 2. And so really what we have is now u to the 8th. So this is equivalent to u to the 8th. But remember, f is in terms of x, not u. So if I want df dx here, or f prime at x is another way that we said that, right? Then I can I can really just do it in two pieces. So I can say df du times du dx. So df du, let's do that one. Df du is a derivative of this function with respect to u, so that's 8u to the 7th power, right? And then the other one, du dx, well, here's u. The derivative of u with respect to x is going to be 6x minus 5, right? So we have that. And then, of course, we can back substitute, and we can put in what u is, whoops, right here. So we can plug that in. So this ends up being 8 times quantity 3x squared minus 5x plus 2 to the 7th power times 6x minus 5. Right? So, and then if we need to do any simplification or things like that, we can. So that's kind of how we did that before. Of course, what did we do? We just said, hey, we're going to act like it's okay, it's a function to a power, so we use the generalized power rule. We drop that down in front, times that thing to the 7th power, and then times the derivative of what's inside, which is right there. So that was the concept way how we did that. This is the expanded way of how to do that. So anyway, and we could have multiple chain rules back in Calc 1 as well. This is not in the notes, but we could say, hey, if I have df dx, you know, I could have derivative of f with respect to u, you know, instead of du dx, I might maybe use in terms of w, so du dw, and then w is in terms of x, so times dw dx. So we could do stuff like that as well, where essentially, you know, these aren't there or cancel out, you know, it's not really what's going on. But anyway, we went through that theory, but we could split it out. If w was a function of x and u was a function of w, then we could calculate df dx via the chain rule there as well. Okay, so now let's go to partial derivatives and see how it works in 3 space. So we got R3 here. We're going to let u equal a function of x and y, and then we're going to let x be a function of 2 other variables, r and s, and y is going to be a function g of 2 variables, r and s. So the reality is, you know, when I have this u here, u is a function of capital F of RS and capital G of RS. So the outputs there are functions of two variables. So let's find out how the chain rule works here. Okay, what we're really going to have here is, you know, if I'm basically on this, I'm looking for the partial of U with respect to R. So it might, and then I might look at, hey, what's the partial of U with respect to S, right? So what we can do is we can use a little tree diagram here. So this is kind of nice. What do we know? We know U, we said, was a function of X and Y. So I can bring this down, use a function of X and Y. And then what else do we know? We know that X is a function of R and S. So we can drop that down. And Y also in this case is a function of R and S. And so what we can really do is kind of drop down along the tree diagram here. So if I go from U to X, hopefully you can see my little dot moving, but I can take the partial of U with respect to X going this way, and then I can take the, going from X to R, I can take the partial of X with respect to R. So remember, it's a partial derivative when there's more than one variable that you have a choice to differentiate with, that is defined in multiple variables. If it's only defined in one variable, it's just a regular derivative with a regular dx. You know, so like dy dx, when y is in terms of x, it looks like, you know, dy dx, because there's only one variable that y is defined in. So just remember that. These are partials here. If I go the other way, if I go from x to x, I guess x to s, that would be the partial of x with respect to s, going this way. Similarly, on the other side, you know, if I'm taking the derivative of u with respect to y, that's a partial derivative. This would be a partial of u with respect to y. And then coming down here, if I keep going, if I then want the partial with respect to r, it's partial of y with respect to r and partial of y with respect to s. Now the question is, how are we going to do this? What are we doing here? So if I want the partial of u with respect to r, okay, here's my u and here's my r's. Notice there's two different places that r's show up there. So what I need to do then is I need to come along the path that connects these together. So u down to r here, and then u down to r here. So basically, to get to the left r, I've got du dx, and then partial of u, excuse me, partial of u with respect to x and partial of x with respect to r. That gets me down this column. And what I'm going to do is I'm going to multiply those together. And then coming the other way, I've got partial of u with respect to y, and then following the tree down, I've got the partial of y with respect to r. So what I can do is multiply those together and then add the results. So the reality is the partial of u with respect to r is going to be given by a theorem. This is a way that we can kind of rememberize, in the words, famous words of Tigger, partial u with respect to x times partial of x with respect to r, and then plus the other branch here, partial of u with respect to y times partial of y with respect to r. Okay, and if you notice, so similarly, you know, this is definitely, you know, the theorem and that we use here. But if you kind of look at it, we can say, hey, it's kind of like these partial of x's cancel out, and I've got partial of u with respect to r when I'm utilizing the x's, but on the other one, you know, the partial y's kind of undo each other. I've got the other part of the partial of u with respect to r. So then what I got to do in the middle is add those together. Okay, so let's do an example. That's kind of what that tree diagram was trying to represent there. you know, we could follow that tree to do the other one as well. But let's go ahead and do the example. Let's do partial. Well, actually, I'm gonna redo that with the other one here. So if I've got u, and u was a function of x and y, and then x was a function of r and s, I'm gonna do the other one here as well. So anyway, so I've got, if I wanted to have partial of u with respect to s, so partial of u with respect to s, what would that be? Okay, so anyway, so basically, how do I get down there? Well, I'm going to take, you know, the partial of u with respect to x going this way, and then going down here, partial of x with respect to s, and so I would need to multiply these together. So that's partial of u with respect to x times partial of x with respect to s. Okay, so once again, du ds, we see the du at the beginning and ds at the end. And then I'm going to add the other ones, which is partial of u with respect to y, and then to get down here is partial of y with respect to s. And so I take those two, multiply them together, and so it's plus the partial of u with respect to y times partial of y with respect to s. Once again, kind of the thing to notice here is, you know, I've got or partial of u with respect to s, so I have it here for the first variable, and I have it here for the second variable. And as you can imagine, if there were three variables, x, y, and z, and three parts to the initial branch, we would have three terms like this that are being multiplied and added. So let's do one and see if we can figure this out. So I'll just do the one that's in your notes to kind of save you some writing here. But we have, for example, if we let u equal x plus 3y squared, and we got x equals r squared plus s squared, and we got y equals e to the r, y equals e to the r power plus, that's the natural log of s, okay? Now remember, the derivative of e to the x is e to the x. The derivative of natural log of x is 1 over x, right? But anyway, we have this. So first thing I'm going to do is, if I use substitution, what would I have? So let's do it kind of the old school way. Let's sub it in. There's too many variables going on, so I want, hey, instead of x, I want r squared plus s squared. So if I sub it in, I've got u equals r squared plus s squared, and instead of y, I'm going to put in e to the r plus natural log of s, so that'll be plus 3 e to the r plus natural log of s quantity squared, right? Now, if I, oh, by the way, what am I trying to find here? I'm trying to find the partial of u with respect to r. Partial of u with respect to r. So that's what I'm trying to find here. So I can do that now. So basically, you know, the original here, that's in terms of x and y, but they're defined with respect to r and s. So really, what I want to make sure, now that I've subbed in, I can go ahead and take this partial, and I can say, hey, the partial of u with respect to r, and we can just do it like we normally do. So r is the variable. Anything else is a constant. So the s terms are considered to be a constant. So the derivative of u with respect to r would be, you know, this one right here, that'd be 2r, right? This would be a constant right here, so that'd be 0. And then over here, I got to use kind of the chain rule. I got to function to a power. So I take the 2, drop it down in front by multiplication. So that'd be 6. That thing to the first power. So that thing is e to the r plus natural log of s. and then times the derivative of what's inside. Of course, the derivative of what's inside with respect to r, right? So e to the r, the derivative of that is e to the r, and the derivative of plus the derivative of natural log of x would be 0 because that's like a constant. So basically, this is it. I've got 2r plus 6 e to the r natural plus natural log of s if you write this in a different order. But anyway, this is definitely doable by substitution, but we're going to get into awkwardness where it's hard to substitute in, or long or lengthy, and we don't necessarily want to do that. So let's also then do this by the chain rule, okay? So if we do it by the chain rule, I don't have those written up, but that's the same as on page 32 in your notes. So anyway, let's do it by the chain rule. Chain rule, so we want the partial of u with respect to r. Well, we're just going to use our, thing here. So you could, once again, use the tree. So if I want to do that, u is defined in terms of x and y. And then x and y are defined in terms of what, r and s. So same deal that we did before. So this is kind of an exact match. So I want du dr, so I got to get from here to here, top to the bottom left r, and top to the other r. So anyway, it's going to be partial of u with respect to x, and then partial of x with respect to r, plus the other way is partial of u, the other branch is partial of u with respect to y, and then partial of y with respect to r. So let's go ahead and do that for this. The partial of u with respect to x, u was x plus 3y squared, right? So if I'm taking the partial of u with respect to x, that's going to end up being 1, because the 3y squared is a constant. And then the partial of x with respect to r, x was r squared plus x s squared, so it's 2r, and then plus 0. And then plus, now I want the partial of u with respect to y, so the x term's a constant, derivative of that is 0, derivative of 3y squared is 6y, times partial of y with respect to r is e to the r, derivative of e to the r is e to the r, and then natural log of s, derivative of that is 0. So we have this, and then of course we can plug in, right, what y is, and so y is actually e to the r natural log of s, and so this is equivalent to 2r plus 6, and then y is e to the r plus natural log of s, and then times e to the r. Normally I would put that e to the r after the 6, and then write the parentheses last. But anyway, that's a mirror image exactly the same as what we got the other way. So that's a good example there. And then so that's what you have in your notes. I'll do a couple of more examples here. Let me just say, if you have, if I have 3 variables, let's just look at one. If I have, let's see, let me use u here at the top. I got u, and let's say that's defined in terms of x, y, and z, and these are all, whoa, I didn't mean to erase that. U is defined in terms of x, y, and z, and then y and z are functions in terms of 2 other variables. We can really pick whatever you want, but let's just keep R and S because that's what we've been using. So R and S. If I want then the partial of u with respect to s, let's just do that one. So I've got my u here, and then here's my s terms down here. Then I'm going to follow the tree branches as a product, and so I'll go this way, add those or multiply those partials together, add it to these partials, multiplied together, added to these partials, multiplied together. So really a kind of a nice thing. So it's going to be partial of u with respect to the first variable x, but then times the partial of x with respect to s, plus the next one is partial of u with respect to y, times partial of y with respect to s, okay, and then plus the last one, these are all pluses, right? We're adding these products together. Partial of u with respect to z times partial of z with respect to s. So ultimately we got three products that we're adding together there. And what's kind of nice, same deal, those kind of cancel out like before, but ultimately you have partial of u with respect to s is remaining, but you got three different branches of where that comes from. Okay, and this does generalize into n variables, etc. By the way, not only could you have n variables underneath the u, we could have m variables underneath, x could be in terms of m variables, and so this generalizes as indicated on page 1013. Alrighty, so let's do an example or two, and then I got my family is apparently ready to hit the road here shortly. So I was just gonna step you through a couple things here. Let's see, and then hit one more example. Well, I did an example of one. Let's do, I kind of want an example with three of them there. That's kind of like number 14. So let me just make up my own example here and hope that it works out. Otherwise, we'll figure it out. So let's do x plus 2y plus 2y squared plus 3z cubed. Let's just do something like this. And if I want, let's say I want the partial of u, and by the way, let's have x and y and z all be defined in terms of r and s. So let x equal r squared, let y equal r plus s, and let z equal it doesn't really matter, 2s. Okay, so we got something like this. So basically, if I want the partial of u with respect to r, let's do that one, partial of u with respect to r. So once again, I can use my little chart. I'm gonna just put it here. So u, we got x, y, z. Instead of writing the whole thing out, I'll just kind of do this, and this is rs, this is rs, and this is rs. We can kind of use that as a visual, going from u to r each way, and then how you get there with the partial products. So doing that, I'm going to have partial u with respect to r is partial of u with respect to x first, and then partial of x with respect to r, plus partial of u with respect to y, partial of y with respect to r, and then lastly partial of u with respect to z, and then partial of z with respect to r. Now I know in the book they want you to do this with substitution as well, I think, maybe not. But sometimes they want you to show substitution as well, make sure your answers match. I'm not going to do that here. I'll leave that to the reader. You're the reader. So good luck, Luke. All right. But anyway, so partial of u with respect to x. Let's go up here. Partial of u with respect to x. Everything else is a constant, so that's 1, right? and then partial of x with respect to r is 2r, plus partial of u with respect to y. The first and last terms are constants, so that'd be 4y to the first, or 4y. And then partial of y with respect to r is 1. And then lastly, partial of u with respect to z. The first two terms up here are constants, so that'd be plus 9z squared. And then times partial of z with respect to r would be 0 in this case. Okay, so that goes away. So really it's just 2r plus 4y. However, we want the partial of u with respect to r. This is not in terms of r, so what we can do here now is sub in. So we're going to sub in what y is, right? And in terms of r and s. So this is equivalent to 2r plus 4 times the quantity r plus s. And then, of course, in this case, we can multiply out. So that ends up being equivalent to, this is 4r plus 4s, right? So that's 6r plus 4s would be the partial of u with respect to r there. So hopefully that helps out. I do want to mention one more thing. If we have u as a function of x and y, and then x and y are only some function of one variable, t. Okay, so this is different. This we were using g here for the, so g of t. We got to be a little bit careful here, because when we do our tree, so we still have x and y here, but we only have one branch coming down from the x and y, and because those are only defined in terms of one variable. So doing this, we've got partial of u with respect to x going this way, but then going from x to t, this is a regular dx dt, because it's only in terms of one variable. Similarly on the right, this is partial u with respect to y, but going down here, this is dy dt. So we need to be a little bit careful on that. So if I wanted, in this case, if I wanted the partial of u with respect to t, not partial, let's see, let me double check this. It's not a partial, because there's only one variable at the end. So the derivative of u with respect to t, the question is, how do we do that? So once again, we'll follow this down. So we got the u here and the t's here, and so the derivative of u with respect to t is going to be given by the partial of u with respect to x times the derivative of x with respect to t. So that's a regular d here for this one. And then plus the other way, partial of u with respect to y. Once again, the first ones are partial because there's two variables to choose from. The last one is a regular derivative because there's only one variable it's defined in terms of. So dy dt, once again, those are regular d's. So hopefully that makes sense.